Right, good morning everyone. Thanks for joining us. We're still waiting for a couple more people, so we'll probably wait a couple of minutes before we kick things off. Just a quick introduction though. My name's Ollie Lewis. I'm a sales consultant at Microconcepts. Joining me today on the webinar is Rickard from one of our partners, Future Group. He's going to be taking us through HSM, which is one of the new products that's come into the product design and manufacturing collection. He's going to show us the workflow through Inventor. It's a plugin that sits inside Inventor, so it's a very nice workflow. So you've got the CAM capabilities actually inside Inventor itself now. We'll just wait a couple more minutes for a couple more people to join us, and then we'll set things off. I think throughout it as well, if you want to just take a note of my email address, if you've got any questions, there is a comment box on the right hand side. So if anything pops up during the webinar, just send over a message and we'll address it at the end. Or if you have any questions that you want to address afterwards, take down my email address and we'll follow it up on everyone who's attending today. Right, I think that's the majority of them, Rickard. So yeah, thanks for joining us, everyone. I'll pass you over to Rickard now. He's going to show us, do a quick introduction to HSM, how it sits within Inventor, and yeah, show you some of its capabilities. Yeah, take it away, please, Rickard.
Thank you, Ollie. So welcome everyone into this webinar, and hope you will find this very interesting and interesting with the HSM product. Before we start, I would like to present myself. So as you know, I work at Future Group and I'm technical sales manager here. And I've been in Future Group for about 2 years, or a little bit more than 2 years. And I'm running the product design and manufacturing collection, of course. And also I work with Delcam CAD/CAM software for more advanced situations. Before I worked at Future Group, I was a global head of CAM development at a dental company called Noble Biocare. And at Noble Biocare, we used Autodesk PowerMill to automatically create toolpath for our 5-axis machines. So it was quite a big challenge to receive a little bit less than 5,000 orders a day and produce all the toolpath for the 5-axis machining fully automatic. Before Noble Biocare, I worked at a company called Protec, and Protec is a master reseller for Delcam software. So I worked as an application engineer there for almost 10 years. And before that, I worked as a designer for plastic products using CAD/CAM as well. So I have about 20 years experience of CAD and CAM. So and I look forward to show you what we can do with the HSM product. So what happened quite recently is that we put the HSM product into the design and manufacturing collection, and we also put the Nastran InCAD in this collection. And this makes the collection really, really strong. In this webinar, we will cover some CAM basics. We will do Autodesk HSM demonstration. I will talk a little bit about post-processor because that is an important part of the process, of course, to customize the G-code to your machine and your controller. We will talk a little bit more about the design and manufacturing collection. And of course, I'll do a technical presentation of the software. When we talk about CAM basics, we can divide manufacturing or subtractive machining into different groups. And with the HSM package, we divide it into 3 different groups. So we have turning, we have milling, and also cutting. So when we talk about turning, then you know that the part is rotating and the tool is almost standing still. Milling, then the tool is rotating and the material is standing still. In cutting, then we have some kind of abrasive material like water cutting or laser cutting, but also smack cutting. but cutting is more or less 2.5D machining. Only in X and Y we can't handle multi-axis cutting at the moment. As you all know, CAD stands for computer-aided design. When we have a computer and do some kind of CAD model or wireframe model in the computer, that's what we call the CAD software. And the CAM software is the computer-aided manufacturing software where we convert the CAD model into a toolpath or a turn path. CNC controller, computer numerical controller, that is more or less a computer that could convert the G-code produced by the CAM package to the machine with linear and rotary axis. So that is our friend, of course, the CNC controller. And to do that, we need a PB, a post-processor, and the post-processor is like a translator, translating the native format inside the CAM package and customize it to fit into a controller or a specific machine. HSM, that is the name of our software, of course, and it also stands for high-speed machining. So we try to keep the spindle speed as high as needed, and also to increase the feed rate in the machine. And by that we can remove material as quick as possible and also get as good surface finishing on the produced part as possible. So what is subtractive manufacturing? Well, it is a controlled way to remove material from a solid block of material, and that could be done with CNC milling or with turning. But in the cutting condition, it is a similar situation, but we need to handle both machine types. On the left-hand side, we can see the adaptive clearing strategy we have in HSM, where we cut with the full length of the milling tool, and we will talk more about that strategy in the demonstration. But that is maybe the best, the most powerful feature we have in the HSM package, and I really like that functionality. If we look into turning, we can divide turning machines into two major sections. One machine type could be a mill turn machine, and that is a CNC milling machine that also have some turning capabilities. If we talk about a turn mill, then it's more a traditional turning machine with some milling functionality. But programming both machine types is similar in the CAM software. For cutting, we have water cutting, plasma cutting, and laser cutting. But in a programming perspective, it's almost the same. It is similar to a 2.5 axis CNC milling. And we rely to some features in the controller to handle the cutting condition. But it's possible to handle water cut and plasma and laser cutting with the HSM product. And also, of course, we can do some wire EDM if that is needed. When I talk about milling, I will talk about a lot of different types of milling, like 2D milling. And 2D milling is when I control the toolpath from a wire in a sketch inside Inventor, and all the toolpath is positioned on the same Z level. If I talk about 2.5D machining, then first of all I have a CAD model, a solid model, and then the 2D strategy will be machined on different Z height, or could be machined on different Z heights in different pockets. But when we do the cutting, it will be only cutting in X and Y direction at one time. If we talk about 3D machining, then we use 3 linear axes in the CNC machine, and that makes it possible to machine curved geometry. So that is the most common machining, I would say. 4-axis tool orientation machining, that is if we have a 4-axis or a 5-axis milling machine or a turn mill machine, where the rotational axis could be positioned in an angle and then we machine 3 axes. 4 axes simultaneously, that will be with the 4th axis rotating during the 3 axis machining. So 4 axis is mode at the same time. 5 axis machining orientation, or as I prefer to call it, 3+2 axis machining. That is when we index the 2 rotational axes into fixed position and then machine normal 3 axis. And the programming way will be similar to 3 axis. It's just a new Z-axis direction and some collision checking. And 5 axis simultaneously, that will be when we use 3 linear axes and 2 rotational axes at the same time. That is the most complicated and most time-consuming way of machining, of course. So when I go out to customers, I meet a lot of different machine types, but it doesn't matter too much. Sometimes I go to customers that use some benchtop machines, very small machines with maybe without a tool changer, and also small stepper motors, not too strong. So then we need to consider the strength of the machine, but it is quite similar to a more advanced machine and strong machine, because we always need to consider the cutting forces in a good way. The second machine here is a slightly bigger machine. It's about 100 meters in the y-axis direction, and this is also a 5-axis machine. It's a head-head machine because the rotational axis is in the head of the machine. The third machine is a more typical 5-axis machine used for mold and die industry. And this is a head table machine because we have 1 rotational axis in the head and 1 rotational axis in the table. Here is an example of a slightly bigger machine, and also there's a small house here, and the operator is sitting in that house and very close to the cutting, where the cutting condition takes place, to control that everything is correct. For turning machines, we can control basic 3 basic turning machines, but also more advanced turning machines with milling possibilities. In this example, there is a turn mill with a double set of spindles. So we can handle stock transfer between main spindle and sub spindle, and we can continue to machine the part in the sub spindle. The last one is a mill turn machine with a vertical mill configuration. So let's look into the Autodesk product design and manufacturing collection. What happened quite recently is that we put Autodesk Nastran InCAD into the package, and also the HSM product. So the Nastran InCAD, that is a simulation product, and it is very generous of Autodesk to put it inside the collection. And I think a lot of customers will find it very useful to do advanced simulation to different designs. Also, we added the HSM product into the collection. Previously, you had a choice to buy or subscribe to the HSM product as a separate product, and then you could choose between the HSM Ultimate and HSM Premium, and that was 2 different levels of the software with 3-axis machining or up to simultaneously 5-axis machining. But today inside the collection we have put the ultimate version. So there is no additional module for HSM. Everything is there already from the beginning. We also have Fusion 360, and as you know, Fusion 360 have some CAM capabilities as well. And good to know is that it is exactly the same HSM module implemented in Fusion 360. But the Fusion 360 in the collection only includes up to 3-axis milling. So there is no 5-axis machining in Fusion inside the collection. With Autodesk HSM, there is also possibilities to run the CAM inside SolidWorks. So you have the choice to run HSM inside the Inventor or SolidWorks. And that could be a situation if you already have a SolidWorks license. Then you can use that license and use the CAM inside SolidWorks. Else, I think it's more preferable to use it inside Inventor. Also, there is a free version of HSM. So that means if you have an Inventor LT license, you can download HSM Express for free. But that is only 2.5-axis machining. So no turning and no 3D machining. And of course, that could be done also to SolidWorks. With the ultimate version included in the PDMC, we have 2 to 5-axis milling, including 3+2-axis milling and also turning. And as said, Fusion 360 is only the 3-axis milling, nothing else. And the same for SolidWorks, of course. So let's look into the Autodesk HSM in the milling section and what kind of functionality we have. And I will start with the 2D strategies. First of all, we have 2D adaptive clearing. So that is a very, very nice feature, and we have it both for 2D adaptive clearing and 3D adaptive clearing. We also have facing, pocketing, profiling, slotting, tracing, engraving, chamfering, that's very important, and drilling and core circular and thread milling. But we will look a little bit more into this during the demonstration of the software. I would like to talk a little bit more about adaptive clearing, just to make it clear what it does and how good it is. On the left-hand side, we have an example of traditional roughing, and on the right-hand side, we have an explanation of the adaptive clearing. So let's look at the traditional roughing. And let's look at this part from the above. And this is actually the milling tool that we can see here. And with traditional roughing, we only machine with a small Z depth at a time. And when cutting in this area, we can see the red section of the tool. That is the section of the tool that is in cut, the load of the milling tool. And when the tool comes into the corner here, we can see that a larger area of the milling tool is engaged into the material. And that is when we can hear the machine screaming a little bit, or the tool could scream a little bit. And also when we have a full wide cut like here, when we go into this pocket here, most likely we have to reduce the feed rate for this section of the tool path, or we need to reduce the feed rate for the whole tool path to make it to work. But the main thing is we only use the tip of the tool. If we look in the adaptive clearing instead, then we try to use as long portion of the milling tool as possible. We try to machine at a much deeper Z level at a time. So maybe we would like to machine with the hole tool engaged with the material. Here we have the same cutting condition as in the traditional roughing, but when it comes to the corner, we start to move the tool in circular direction. And by that, we maintain the cutting condition also in the corner. And we don't hear the milling tool screaming that we can do with the traditional roughing. And the same thing, instead of a full wide cut, we start to mow the tool in rotational mows, and that will give us a very smooth and a very, very controlled way of moving the milling tool. So by that, we will remove the material much faster during machining, because we can increase the speed of the machine, because we know the cutting condition from the beginning. It will never change. And also we will extend the tool life because we're using the whole length of the milling tool and we have full control of the cutting condition. So this is a really, really nice strategy. And if you try HSM, you should definitely go for the adaptive clearing. If we look into the 3-axis functionality we have, yes, we have the adaptive clearing, of course. We also have horizontal and parallel strategies for shallow areas. We have contour and ramp strategies for steep areas. Also morphed spiral is good for steep areas. And we have some radial projection, morphing, scallop strategy, and pencil tracing for finishing. And the pencil tracing is for rest machining. All 3-axis toolpath could be used for 3+2 machining as well. So it's not more difficult at all to machine 3+2 axis than 3 axis inside the HSM product. For the 5-axis functionality, we have a swarf cutting strategy, and that is when the tool is machining the whole length of the surface with the side of the milling tool. We have multi-axis contour machining, and also we have automatic tilting for the router axis. By that we mean that if you machine a 3-axis toolpath and activate the automatic tilting functionality, the toolpath will be calculated 3-axis when it's possible, and where we need to tilt the tool because of a risk of collision with the tool shank or the tool holder to the CAD model, the system will automatically use the rotational axis to avoid a collision. And that is the best way of machining, I think, to machine as much as possible 3-axis and only use the router axis where needed. We also have the 4-axis wrapped toolpath. So by that we mean that for all 2.5-axis strategies, we can apply it as a 4-axis simultaneously toolpath if we have a mill turn machine. If we look into the turning in the software, we have a lot of turning functionality. We have face and profile turning, groove turning, part cut off, and by that we also have a stock transfer to the subspindle. We have thread milling, drilling, boring, and chamfer turning. And the chamfer turning is similar to the chamfer milling. It's the same purpose. We have some additional functionality. Good to know. We have a stock model with rest machining options. That means that it is possible to design your stock model as a part file, and you can secure that you only have rest machining inside the designed stock model. We have an automatic tool holder collision avoidance. That is when we do a 3-axis toolpath with 5-axis functionality as an add-on. Slope-based machining, we have probing. So it's possible to probe, if we have a probe in the CNC machine, to find the center of a hole or find the center of the stock to machine in the correct place. We have some automatic setup sheets, and those are also customizable if needed. Stock simulation and verification, so we can do some collision checking to the stock. And also we have a tool length optimization in the software. And that is also very nice, so we can optimize the tool length so we know what we require for tool length when we should do the setup in the machine. Post-processor, yeah, that is a very important link between the CAM software and the CNC controller. And with the HSM product, we have an open post-processor, and that means that it's possible for anyone to customize the post-processor. But if you buy a post-processor from us, or if you download a free post-processor from Autodesk library, it is possible to adjust it by yourself, or we can help you to adjust it. So I think it's time to do a technical presentation of HSM, and I will use a product from a skateboard. I think this is an interesting part. It's a swing axle, and the good thing with the swing axle is if we think we should design a swing axle, we can also use Nastran InCAD to do the calculation, the simulation of the part. And we will see the benefit of having a CAM software inside the CAD system, because everything is in the same software. And by that I mean that if we modify the design of this swing axle, we can just apply the change also into the CAM calculations. So if we have a CAM calculation of a part, we can just modify the part and then recalculate the tool paths more or less automatic. And that's when we really save times with the CAD-CAM software. Okay, so this is an example of Nastran InCAD with a dynamic simulation of the part. So on the right hand side, the small pocket is slightly smaller to make the product strong enough. In HSM, in Inventor HSM, I will do a setup of the product in this vise like this. And of course, this product needs to be machined in a two-tempo situation, so we need to move it 180, but I will focus on the first step in this demonstration. So let's close this presentation and switch into Inventor HSM instead. So hopefully you recognize Inventor, and as you can see, we have all the 3D and every features in Inventor. But with Inventor HSM, we have one extra tab here called CAM. So if I click on the CAM tab, I will see all my CAM features, all my strategies. So that is very easy to access, and it's possible to switch between the CAM and the CAD at any time. So first of all, before I do the setup, before I describe where I have material, I would like to show you the tool library. So most likely you will create a tool library by yourself, and that could be the standard tools you have in the machine. And with the tool library, in the tool library, you can have the milling tool, and you can define the diameter, the type of the milling tool, and you can also define the cutter from a part file. So it's possible to design the tool inside the inventor and save it as a part file and then load it. And that is excellent if you have a tool with a special profile like this. With the tool, we save all the cutting conditions, and we can also save the tool holder and everything that belongs to the tool. Good. So when I should do some machining of this part, I have already done an assembly of the part inside to fit it in the vise. But it doesn't matter if I would like to machine from an assembly file or a part file. It works exactly the same. So that could be good to know. It doesn't matter. You can machine on a part file with a lot of parts, and you just create a new setup for every part that you would like to machine. So when I click on the setup icon here, HSM tries to help me. And the best way to help me is to create a stock all around the parts I have. But that is not correct in this case. So I unselect the model and say, this is the model that I would like to machine. And then directly the system creates a new stock for me just with the max values out of the parts. Also, I need to define the Z-axis because with this part, the Z-axis is aligned in this direction because the part was designed that way, and that is not correct for machining. So then it's possible for me to select the Z-axis and also select the X-axis. So if I simply click on a face, then we can see that the Z-axis is aligned perpendicular to that face. So if I click on this face, then we can see that the Z-axis is perpendicular to that face. But now I would like it to be perpendicular to the top face. Also, it's possible for me to decide where I would like the 0 point. And I prefer to use the model box point option. So maybe I would like the 0 point at the top and center of the part. It's up to the user, but I think that could be good in this case. And also it is possible to define what is the fixture. So with this assembly, I have parts like this that I would like to define as my fixture. And by doing that, HSM knows where we should not have a toolpath, so we can avoid those areas. In the stock tab, well, there I can add some extra material. So, for example, I can add some extra material downwards to be able to fix it in the vise. Maybe 15 millimeter extra. And then I click OK. I'm happy with my setup. And first machining strategy I would like is a face milling. I just want to face the top of this material to the correct height. If I look into my 2D strategies, I select the face milling. And then I can see a form, and the form always looks the same. It's no difference. It contains 5 different tabs. And the first thing I need to do is to select the milling tool. And when I click the milling tool, then I will be directed directly to the tool database. So maybe I would like a 16 millimeter tool or a 32 mil face mill, but maybe I select the 16 mil tool not to overload the part with the cutting force. I click OK, and then we can see that the feeds and speeds are loaded directly here. I could walk through all the other tabs here, but I tried just to click OK directly and calculate the toolpath. And we can see directly that I get some blue and green lines on the screen, and that is the cutting section of the toolpath. Blue lines, that is cutting into the material, and green lines is the link or connection between lead out and to the lead in. And that could also be modified, of course. Just to make it easy to understand what's going on, I can simulate the toolpath, I can turn on the stock, and I can play the simulation, and we can see directly on the screen the material being removed. And we can see that we are cutting to the CAD model. It's blinking a little bit because they are in the same level. Of course, I can look into the statistics. I can see the machining time, I can see the machining distance, and a lot of other information, and I can close the simulation. But to be honest, it was quite easy to create this face milling. I just selected the milling tool, and then I clicked OK and calculated the toolpath, and the toolpath looks okay. So maybe you think it was too easy, but I can show you how HSM is working in the background. So if I edit this toolpath and go to the passes where I define the step over, the step over is 9.6 millimeter here. But if I right click and say edit expression, here I can see I use the tool diameter parameter. So this means I load the tool diameter in here and multiply it by 0.6 and calculate this value automatically. So if I change to a different milling tool, this value will automatically be updated. And by setting up HSM this way, I can learn the system how I would like to machine. So that is something I talk a lot of when I have training for customers, how we customize the system to make it as easy as possible to use. So for me, when I have set up the system, I simply selected the face milling, I selected a milling tool, and then calculated the toolpath. Simple as that. So the next step for this part could be to do a roughing or adaptive clearing outside the part. So I select a 2D strategy, a 2D adaptive clearing. And once again, I would like to select a milling tool, and I select the same 16 millimeter flat tool. And then I need to tell the system where I would like to machine. So if I select the contour of the part, the system helps me to understand what will be calculated. I get some blue region that explains this is the area that will be removed. And if I click on the tool path heights form, here I can define on what level the toolpath should be calculated. So if I look into the bottom section, bottom height, it will be calculated from the model bottom with a negative offset of 0.5 millimeter. But there is a lot of option to configure it. If I calculate this toolpath, we will see an adaptive clearing, and it will be slightly more lines, of course, than previous toolpath. But here we can see the circular shape of the toolpath into the corner. But let me simulate this toolpath also to make it clear how it works. We can see we're running around the part like this, and then we will start to work from outside and inwards. I can speed up this a little bit. But this is a beautiful way of machining, and the sound of the machine will be constant during the cutting. And it's also possible to define the smallest radius and a lot of settings if we would like to do that. Worth to mention is also on the bottom side here in the simulation, this green section here. If we get a collision, it will be a red section here, and that will highlight for us that we have a problem. It's also possible to stop the calculation on a collision, so we can take an action out of that. So we have the face milling and the roughing, and maybe we would like to get the machine up and running with those two toolpaths before we continue the CAM calculation. So if I select those two toolpaths and click on post process and click on post, and I have a name of the toolpath and I replace that toolpath, and then directly I have the G code for my machine. So we also could see that the calculation for the post processor is really fast. There's no waiting for the G code. It comes almost directly. So that is also a nice feature of HSM. So the next thing for this part, it could be to machine the inner pockets. And that could be done by using a 3D adaptive machining. I would like to use a slightly smaller milling tool, so let's select a 6mm milling tool. The cutting data is loaded once again from the tool database. And for this strategy, I need to tell I would like to machine in those 3 areas. Just a quick look into the heights, and I can see that the bottom height of the toolpath is calculated from the model bottom. So now we get the set height and everything from the CAD model. So let me click calculate for that one, and we can see on the screen that we have the 3-axis adaptive clearing in those pockets. If we simulate this toolpath, we will see that the simulation will start with a helical toolpath down to full depth, and then we will work out of this hole to remove the material. So that is the way of working in pockets with the adaptive clearing. So I think we can speed this up to the end, and then we can close the simulation. And I can see on the green bar that there is no collision. The tool length is correct. So that is nice. Good. The next thing I would like to do is to chamfer the part. And that is an important part of basic part like this. If we have a CNC machine, I think we should chamfer the part inside the milling machine. It could be done manually as well, but the milling machine will do it better for us. The product will look nicer, and I think it will be quicker as well. So in the 2D strategies, we have an option of 2D chamfer. And with the 2D chamfer strategy, I will use a spot drill like this, 90 degrees angle, and it could be flat in the bottom as well, it doesn't matter. But the chamfer strategy is used when the CAD model does not contain a chamfer, so it is a sharp corner in those areas. Then it is possible to say that I would like to have a chamfer width of 0.2 millimeter. Maybe I would like a chamfer tip offset of 0.3 millimeter, and I will explain it when I simulate this toolpath, what the chamfer tip offset is. Calculate this toolpath, and we will have a chamfer of those edges. So let me switch to the simulation, and this time I turn off the stock, and I hit play and stop the simulation, and we can see that we have a chamfering of the part here of 0.2 millimeter, I think we had. and chamfer tip offset. That is a possibility to machine with somewhere on the edge of the tool. So now we have offset from the tip to this contact point of the milling tool. And that could be a good way to avoid the tip of the tool. Also, if you damage the tip of the tool, you can still use it by doing additional offset of the tip. Also, it's possible to do a chamfering when the chamfering already exists on the CAD model. And I prefer to use the 2D contour for that. So I need to select the spot drill for that. And when I select the spot drill in the 2D contour strategy, the chamfering will pop up here. So I could say I don't want any additional chamfer width. So then it will be machined as designed. And I could say this is the chamfer edge and also this is the chamfer edge. You can see now that the contour looks really strange, but that is because I have a tool orientation activated. So by untick the tool orientation, everything will be correct again. Else the said tool axis was programmed for something else. So when I calculate this chamfer, if you look on this icon here, you can see there is a green mark here. So I didn't get the toolpath here, but I would like to show what the system helps us with. There is an information that there is something in the log file. And if I look in the log file, it tells me that the given lead parameters would cause a collision of the tool with the CAD model. So it didn't calculate the toolpath. So if I simply unselect the lead entry and recalculate the toolpath, then I can see I get the toolpath. So that is really nice that I can see the collision directly when I try to calculate the toolpath. I don't need to simulate the toolpath, or I don't need to machine the part to find the collision, not even on the 2.5D strategies. That is nice. When I'm happy with this, I can select all the toolpath or the setup. I can say I would like to post-process everything, and then directly I will have the toolpath or the G-code like this. So very fast to get the code out to the milling machine. When I do the post-processing, it is possible to open the config. If I open up the config, it means I open up the post-processor. So this is the code that would generate the G-code. And yeah, it's a lot of functionalities, a lot of functions that handles this, but everything is open to modify for anyone if you have the knowledge. But of course, we can help you to do that customization. And I think that is the most common also. There's also an option page here when I'm doing the post-processor that is customizable. So I can customize a lot of stuff. It could be anything. It could be a loading part with the robot. It could be open doors, closed doors. It could be just anything. Good. So I think this part is almost finished. I will only create one more toolpath, and that will be the profiling with the profiling tool on the outside. So I have a customized tool here. I designed it with Inventor, saved it as a part file, and loaded the part file when I defined the milling tool. And I will select this outer profile and calculate the toolpath, and then we have the profile with this tool. So it's really nice that we can use a customized profile of the milling tool and match it to the CAD model to machine the correct profile. If we simulate all of the toolpath, and I will turn on the stock again, and I will speed up the simulation because this time I only would like to see the final result. And maybe I would like to see the toolpath as a tail. That's less messy. And here it's possible for me to activate the part comparison. So the part comparison, it will compare the simulated model and the CAD model. So where I have the blue areas, that's where I have material left, and where I have sorry, excuse me, where I have the gray area, that is where the machine is finalized. So we can see we have some material left on in the holes that is angulated, and also on the bottom as expected, but everywhere else the product is finished. That is nice. So let's say we have post-processed the code and everyone is happy, but then by sudden our designer comes and tells us we need to make a design modification of this part. Maybe we need to modify the size of the holes to make it stronger or make it lighter. So because this is an assembly, we could edit this part file.
Yeah, perfect. Thank you.
So if I switch to the CAD model functionality in Inventor, it's possible for me to simply activate some cam changes I've done in beforehand, but it could be done by using all the features we have in the 3D model section here. But now I just activate some modifications, and as we can see, the holes are now a little bit larger. I can undo this. You can see that the holes changes in size, but it could be just any kind of modification of the product. So if I say that we return to the assembly and we return to the CAM tab here, we can see that all of the toolpath gets a red cross over the icon. If I click on the toolpath, I can see that everything is still here. It still is possible to post-process the toolpath if I would like to do that, but the red cross means it is not up to date to the latest design of the CAD model. So what I need to do now is simply to click on the generate button here. That means that I will calculate the toolpath once again with the existing CAD model. And because that everything is defined inside the toolpath strategies, I don't need to modify anything. I simply click on this button and everything will be calculated at the same time. So please look at the toolpath strategies. When I click on the bottom, you will see that it calculates at the same time all the strategies. So I use all of the cores in my computer at the same time. So you can see that everything is calculated, and it's calculated really quick. So we have the face milling, we have the 2D adaptive milling, 3D adaptive chamfering for the new geometry, and everything else. So now I just need to post-process it once again, and we can start the machine with a new design. So that is really strong functionality when we have the CAD and CAM in the same software. It's very easy to update the product design, and also we know what version of the CAD model we use when we generate the toolpaths. So I think this is about what I would like to show you in this basic HSM demonstration. I hope you had some new insight to the CAM software, and you're absolutely free to contact me or Ollie after this presentation.